crazy times is that it's a lot easier to give talks all over the world. So it's my absolute pleasure to be here giving a talk in London, but from the comfort of my own office. Yeah, so, okay, I'm going to be talking about anomaly detection, astronomical data. I'm very aware that this group is probably not experts in machine learning, so I'm going to have a little bit of an introduction to machine learning before I go into all the research. So apologies to those of you who are experts. You have my complete permission to sit and answer emails. And this is work that I've done. Let me see if I can get a pointer. Here we go. This is work that I've done in collaboration with quite a few people that I've just mentioned here. Okay, so let's start by setting the stage. So there's two really big telescopes coming up that I'm really excited about. And you all will know both of them quite well. The first is the Vera C. Rubin Observatory, what used to be called the LSST. And this is a really exciting optical telescope. It's going to be able to take images of very large field of view, very deep and very fast. So the kind of science that this thing enables is quite impressive. And it's trying to do all of the science with this crazy 10-year survey. But I think for me personally, the science case that I'm most in awe of is transient science. Because this is a beautiful simulation where every single dot represents a supernova. And by the end of the 10-year survey, we're expecting sort of 500,000 to 1 million really well-measured light curves of supernovae. And to put that in context, the first dark energy discovery was done with like 40 supernovae. So we're really doing quite a step up in terms of data quantities. But this isn't even the impressive part. The impressive part is because the Rubin Observatory is so large area, so deep and so fast, the number of transient alerts that it will deliver every single night is about 10 million. So 10 million times a night, it sees something change. And now, I mean, half of those are going to be things like artifacts, but half of those are going to be real astrophysical phenomena. So that's one question. How are we going to handle 10 million transient alerts every night so that we can do really cool science? The other telescope that I'm interested in and also slightly terrified of is, of course, the Square Kilometre Array, which this group is deeply involved in. And when we talk about the data rates for the SKA, to me, I think the most scientifically accurate term that you could use is stupidly large. But that's okay. The raw data is completely insane, but even the reduced data, we're talking about surveys of 1 billion galaxies. In the time domain, there's thousands of coherent and incoherent radio transients. So the SKA also represents this incredibly rich data source, but also incredibly terrifying. And we're already starting to be pushed. So obviously, I'm deeply involved in MeerKAT, which is a South African precursor telescope to the SKA, which is 64 dishes, radio dishes. And even though 64 dishes is not as large as the final SKA array, we're still starting to be pushed by the data that's coming in from MeerKAT. And the kind of old-fashioned ways we have of dealing with this data just isn't working anymore. And MeerKAT's just one example. There's also LOFAR, ASCAP. There's a bunch of examples in the optical. So we're starting to have to change the way that we actually do science. So I like this image. We're facing a data explosion. This is really what it feels like is coming. So this is where machine learning comes in. So let me give you a very brief, easy introduction to machine learning, the way I see it anyway. So first of all, when people talk about machine learning, they're often talking solely about supervised machine learning. And we're going to get to the other side of it, unsupervised machine learning, a little bit later. But this is often the easiest starting point anyway. So here we have a very typical example problem where you have some data and you have a classification problem. So these objects belong to one of two classes, the circles or the crosses. And what you want to do is try to find a model that divides the circles and the crosses so that for any new data point, you can tell which class it belongs to. This is a very typical example problem. Now, as physicists, we might look at the data and hypothesize some model and then fit the parameters and then we're done. Machine learning works a bit differently in that it tries to learn that model automatically, right? So, and the way it's able to do that is if you have some training set, which is the supervised part. So if you have some data for which you know whether it's a circle or a cross, you have the training set, and it allows the algorithm to automatically learn this model so that for any future data, you're able to classify it. So to put it concisely, it's a way to automatically learn a model that maps inputs to outputs. And I hope that that kind of demystifies it, because this is sort of the thing that we've been doing for years. This is just an automatic way of doing it. This is an image that it's actually an exercise I give to my students when I teach them machine learning. This is the simplest neural network that I could think of. So a neural network is arguably the oldest machine learning algorithm, and certainly it's the most popular, especially at the moment. And what you have here is some data, which are your inputs, and you're trying to map your inputs to outputs. And what's here in between is a hidden layer of neurons. So the neurons are a way of connecting these inputs to outputs. And how is this connection made? At the end of the day, you can write down an equation which describes this whole network. So this is the equation. It's complicated and nonlinear, but it's not that complicated. And this is, for any given input, this will give you the predicted output. And the training of the network, it would involve learning what these weights are, these W's. So I just put this up to show that even though these algorithms can get incredibly complex, fundamentally, this is the thing that they're doing. They're learning these models that map inputs to outputs. Okay, so just some definitions. Well, okay. This is more than just definitions. This is kind of the process of machine learning problems, like step by step. What do you do? The first thing is that when it comes to machine learning, you always start with your data. There has to be some data, otherwise, there's no way to do machine learning. It's a completely data-driven tool. But often these data are very complicated, very high-dimensional, and maybe difficult for these algorithms to ingest. And that's where this important step of feature extraction comes in. And it's a way of often reducing the dimensionality, but the key thing is we want to extract something from the data which we think somehow describes it in a kind of more succinct way. So I'll show you a few examples of those, but here, just from kind of real world examples, here's an example of a fingerprint. Now, we know we've had fingerprint recognition for many, many years, but this is one way you can automate it. So a fingerprint is a very complicated data set. This is an image. It may have hundreds or thousands of pixels. This is actually technically very high dimensional. But what we know about fingerprints is there are these important points called minutia points. And they're the parts that really matter. What the fingerprint does at those points is the main description of it. And so you can build this minutia map and basically translate it into just a set of fairly simple numbers. And this you can give to a machine learning algorithm to very accurately identify fingerprints. So we've taken our domain knowledge, what we know about fingerprints, in order to reduce this very complicated data set down to something simple that an algorithm can understand. Then we have two branches of machine learning. The one is when you have labeled data, and the one is where you have unlabeled data. So what I've described to you so far would all have been cases with labeled data. And this is what we call supervised machine learning, and this is unsupervised. So actually, most of my talk will be about unsupervised learning, but we'll get to that in a little bit. And just to let you know that there are kind of two branches, again, of supervised learning. One is where you have categorical data, which is most of the things that I've demonstrated up until now, which is classification problems. Is it a dog or is it a cat? And the other is where you have continuous data, which is regression problems. And a very common one in astronomy is, for instance, predicting photometric redshifts. So the branch that I'm the most interested in right now is unsupervised machine learning. And this is this very interesting and difficult problem of what do you do if you don't really know that much about the data and if you don't have any labels? There's far fewer examples of unsupervised learning. If you read the literature, 95% of papers, maybe more, 99% of papers are about supervised learning, because it's quite hard to think of what you can do when you don't have any labels. But there are basically two main branches. The one is clustering, and this would be where you maybe don't have labels for your data, but you can perform clustering algorithms to see if there's some kind of structure in your data and try to learn something about it. So this is an example of Wikipedia articles where you can see that there are some quite clean clusters. And when you go back and you check a few examples, you realize, oh, well, these are all the disambiguation pages and these are all the film pages. So you can start to learn something about your data before you've managed to build any training sets. And the other branch is anomaly detection, which I'm not going to talk about now because I'm going to go into great depth in the last part of the talk. Before I go on, I don't know if there's any quick questions. I can't actually see any chat, so if there are questions, somebody would have to interrupt me. Good, okay. Let's get on to the science. So I've worked for a few years now on the problem of supernova classification. In a way, this is a small component of the issue that we're facing with Rubin Observatory, where there's 10 million alerts a night and 1 million supernovae, and we have all this beautiful data. But the problem is we don't know for sure the type of each of these transients without a spectrum, and it's just takes up way too much telescope time to try to take a spectrum of every single object that is detected. So in order to do cosmology, to make use of this data set, we have to be able to classify supernovae without spectroscopic follow-up, or with very limited spectroscopic follow-up. And why is this a problem? Well, of course, we know there's really two types of supernovae. There's the ones that are useful for cosmology, then there's all the other junk that nobody cares about. I'm just kidding. Core collapse supernovae are very interesting astrophysical objects, but we are mostly interested in the type 1As if we want to do cosmology. And the core collapse supernovae are bad contaminants. They would cause biases in the cosmological parameters if we included them in our data set. So we have to try to accurately classify these different classes of supernovae. And the kind of data that we have looks a bit like this. So this is the supernova light curve, so your brightness as a function of time in different filters. And this is basically all we have. And we'll have some spectroscopic data for some of the supernovae, but it'll be a very small fraction. And we have to somehow use that small fraction to train a machine learning algorithm to actually do the classification. And so just to give you a brief idea, so we explored a bunch of different feature extraction methods for this problem, some of which work better than others. And these plots, I'm going to be showing a lot of these plots. They're called TSNE plots. Don't worry about the complexity of how you create them. They're basically a visualization of very high dimensional spaces that are mapped onto these low dimensional spaces such that nearby points in the high dimensional space stay nearby in the low dimensional space. So in other words, if you see these colors separate very well in this plot, they should separate very well in the high dimensional space as well. So you'll see a lot of these axes are completely arbitrary. They're just visualization tools of the data. Okay, and I mean, there's more details in the paper if you want to have a look, but by now this is old news. What's the new stuff we're doing? Well, just to mention that this paper that we put out doing machine learning for supernova classification was on a pretty simple set of simulations. It worked pretty well. We were greatly challenged by a much more realistic set of simulations, which is called the plastic challenge. It's spelled very strangely. And these are simulations of the supernovae that we're expecting to get out of the LSST survey. So the data is very difficult. And one of the things that we had to do, or all of us, or not just our group, but all the people working on this problem, is to figure out how to handle the fact that we're only going to be able to follow up the really bright supernovae, so the more nearby ones, because it's very expensive to do spectroscopic follow-up for the fainter ones. And that means our training set is biased. And now there's one thing with machine learning, it's good at interpolating effectively, it's bad at extrapolating. So if your training set doesn't look a lot like your test set, it's not going to do a good job. And so we had to do what's called data augmentation to improve this. And this is work led by a very, very bright PhD student, Katerina Alves at UCL. She's supervised by Hiranya Paris. She's not quite at the phase of looking for postdocs, but definitely keep an eye out for this one. I think she's going to be a brilliant researcher. And so she's done some great work and just shows how important augmentation is. This thing is called a confusion matrix. If this whole diagonal was 1, it would be 100% perfect. So it's basically saying, of all the things it thought was a type 2 supernova, what fraction actually were type 2? Well, 42% is not great, but then when you do augmentation, you start to get something that looks a little bit better. And even sort of state-of-the-art algorithms, this is still a very hard problem, and getting close to kind of 100% on this diagonal, you know, none of us have been able to quite get there. But anyway, so this is the work on supernova classification. And I don't actually want to go into this, but just to highlight another student, this was my master's student, Camille Suknunan, who's now doing a PhD at Imperial, who basically applied the same thing to radio transients, which is impressive because, you know, these things are really different. They vary on different time scales. This is a variable, and this is a tidal disruption event. So these are totally, you know, weird, disparate, different types of objects. But the same algorithm was actually able to do a pretty good job classifying them. And the ones that it struggled with, it turns out, if you add optical data to the radio data, then you get a very large improvement. So this was just a very brief introduction to some examples of, well, really one example applied to different data sets of supervised machine learning that we've worked on. What I'm really excited about at the moment is anomaly detection, but I'll pause there for a second just in case there are any more questions or any questions. Alrighty. Cool. Okay, so let me talk to you about what's got me really excited at the moment, but is also a very interesting and challenging problem, and that is anomaly detection. Okay, so what's an anomaly? I think we all have an intuitive knowledge of what an anomaly is. It's anything that's unusual or rare, anything that's very much the minority, very different from the norm. And some examples of this in astronomy are things like strong lenses, where in a huge survey, you might only find a handful of strong lenses. These are rare objects. Or gravitational wave events, or fast radio bursts, or actually, you know, these are maybe not as rare as we thought. But these are examples of events that are rare, but I call them, what we call them, known unknowns. These are things that we're looking for, right? They're rare, they're anomalous, but we know about them. The thing that's got me really interested is the unknown unknowns, new anomalies, new phenomena that nobody was expecting. And traditionally, unexpected discoveries have been made when a very intelligent human being, like Justin Bell here, looks through a whole lot of data and notices something unusual, something unexpected. And the question that I ask myself is, how are we going to do that? How are we going to discover new things when there's 10 million transient alerts a night, or when there's 1 billion galaxies in the data set, when most of the data probably won't even be seen by human eyes? how do we still make sure we're not missing out on exciting new discoveries? And so that's where anomaly detection can come in. And this is a branch of machine learning called unsupervised learning. And now the way these algorithms tend to work is because you don't have training data. By definition, you can't have training data because you don't know what you're looking for. You're looking for the unexpected. So you give it some data. And the algorithm, instead of trying to learn a model for classification, for instance, it tries to learn a model which describes the norm. So it describes normal data. And then when you give it a new object that's quite far away from the norm, then it gets a high anomaly score. So that's sort of roughly how these algorithms work. So just here's two examples for a little bit more detail. So I'll start with, these labels are in the non-intuitive positions. This is isolation forest. And it's based on a very well-known machine learning algorithm, a classification algorithm called random forest. And basically what it does is it looks at the data, it looks in feature space, and it tries to use a series of splits, so a series of decisions on each of the features, and it tries to isolate every single point. And the idea is that this point, because it's in amongst many other points, it's quite difficult to isolate. You need a lot of cuts. You need to first cut here, and then you cut here, and then you cut here, and here, and here. So it's quite deep down a decision tree. Whereas this point is, like this one. This one is quite unusual, quite far from the norm. And so you only need basically 2 cuts, and then it's on its own. And so it's able to give an anomaly score that way. Then there's another algorithm called local outlier factor, which is a density-based algorithm. So it basically just, for any given point, it sort of looks at its nearest neighbors and calculates the sort of average distance to nearest neighbors, with the idea being that points that are very far away will tend to have a much larger average distance to its neighbors. And it's obviously simplified, but that's the basic idea. So these are just 2 examples of anomaly detection algorithms. And in the group, so I just left the SARAO data science group. It was when I started my new job, but I did a lot of work with them. And in our group, we also developed 2 new anomaly detection algorithms. This one called BADAC is quite interesting in that it's a Bayesian anomaly detection algorithm that can actually incorporate uncertainty in your data and give out probabilities that are quite meaningful. And it's a simultaneous classifier and anomaly detector. And then this one developed by the group is called DRAMA, which is a deep learning based anomaly detection. So probably all of you, most of you would have heard of deep learning, but it's a particular branch of machine learning that uses very deep neural networks that's really done an amazing job over quite a range of difficult problems like image recognition problems, for instance. So this is basically a deep learning approach to doing anomaly detection. So yeah, if you want any more details, obviously these are the papers to have a look at, and you can always ask me. So these are some examples of anomaly detection algorithms, how you might detect these anomalies in the first place. And if you have a data set of 10 million objects, maybe you could cut it down to 1,000 interesting things to look through, or 10,000 interesting things to look through, which means that you as a human are able to hopefully make some discoveries from a much smaller subset of the data. The problem is, or the interesting thing is, anomaly detection alone isn't actually enough. So here's some examples, which I'll mention again later with another student that I worked with. And she was working with this deeper, wider, faster survey, which is a fast transient survey trying to basically detect rare and interesting transient events. And so she had, I don't know, 60,000 light curves, I think. And we ran an anomaly detection algorithm on them. And we found some interesting things. But these things are instrumental effects. And these things are real sources. They are both anomalous, but these ones are interesting and these ones aren't. And the other interesting thing about this is that while we may be only interested in these sources, if you were someone who was, for instance, responsible for for data quality, you might actually be interested in the instrumental effects. So, and if you're looking for peculiar supernovae, you don't care if there's a weirdly behaving variable star. So there's kind of a subjectiveness as to what's actually a relevant anomaly versus an irrelevant anomaly. And so what we wanted to do is build in a layer of what's called active learning. So this is where you combine the kind of the intuition and the expert knowledge of a human with the raw processing power of machine learning. And it's kind of a best of both worlds approach. So in putting all these pieces together, we developed a framework called Astronomy. And I think I'm the most proud of the name. So what is this thing? So it's got a Python backend that takes in your data, and it can work with images, light curves. It can mostly work with spectra, basically any kind of astronomical data you want to give it. It can do feature extraction, which you remember we talked about at the beginning, which is a way of reducing the complexity of the data. And this is a very important step for anomaly detection. It will then run some anomaly detection algorithm. And this is the really interesting bit, is that it performs active learning. Okay, so all of this up till here is just pure Python backend. But in order to get the human interaction, we built a JavaScript front end. So it's basically got a web interface that looks like this. And you can really quickly go through some data and add labels to it. So you can basically rank it based on how interesting this particular object is to you. And so it forms almost like a recommendation engine. Like if you've ever watched Netflix or been on Amazon and it says, oh, I think you'd like to watch this or buy this. And it's usually terribly wrong, but it tries. So that's the idea behind Astronomy, is that it will learn your preferences and with a very small amount of training data. So, I mean, most machine learning algorithms might need thousands of examples, but with this, you can do pretty well with just maybe 50 or 100 examples, which only takes a few minutes to actually label. And then it prioritizes objects that it thinks are actually going to be interesting to you. Okay, so let's see it in action. So I used a data set called Galaxy Zoo, which is from mostly SDSS and a couple other telescopes. And it's a very nice data set of resolved labeled galaxies. And here I'm stepping through just some examples of random sampling of galaxies. And you see that most of these are ellipticals, spirals, kind of boring galaxies. But if you run the anomaly detection part, so the machine learning, and you rank the entire data set, which is about 60,000 objects, from most to least anomalous, then this is what you get. And what you can see is that these are looking much more interesting now. There's some mergers, there's some tidal tails. So it's doing a pretty good job of prioritizing things that have unusual morphology. But you'll notice that there are still things like that or like this, which are artifacts, and they're not of interest to me. And you can see that these numbers keep changing. It's because I'm labeling them. So I'm giving them a score out of 5, where 5 is the most interesting objects. I then run the active learning, and what you see is a lot of the same kind of objects, so the mergers and the tidal tails, but the artifacts have become a little bit more suppressed. So we don't see them so high up in the list. And you can be even more specific than this. You know, if you see a particular object, you're like, that's really weird, I really want to find some more like those, you can label all of those ones as really interesting, and it will rank those much higher. So this is just on one slide, so you can just get a feel for it. These are the random examples. this is when you don't have active learning. So you can see particularly these artifacts. And then when you apply active learning, and here what I've actually done is I've specifically shown the top ranked objects not seen by a human. So these are what the algorithm would recommend to you that you haven't seen yet. So these would be Netflix's best shows that you haven't watched yet. I think it does a better job than Netflix, but anyway. Okay, and just to be a little bit more numerical, this just shows, it's difficult to really evaluate how effective the anomaly detection is, especially when it's actually quite subjective. But basically what we've done here is shown if you go in the index through the ranked list, so this is the first, what it thinks is the most interesting object, and then so it goes. And the number of objects that are actually classified as anomalies by some classification scheme we had, which is pretty subjective. First of all, you can see it does better than random, yay. But then the active learning does improve, but particularly early on in the ranked list. And so what this means is if you only had an hour to go through the Galaxy Zoo data, you wouldn't have to look through 65,000 examples to find some interesting anomalies. Okay, so this was very nice. Oh, maybe I should pause for a second again. Okay. So this was good, but the problem with this Galaxy Zoo data is, as I said, it is quite subjective as to what's interesting or not. And we don't really have a good ground truth to compare against. So what we did was we made some synthetic data specifically to see if our active learning was working as we wanted it to. Okay, so what you're looking at is we made some data that kind of looks a bit like transients, a bit like light curves, but it's not realistic at all. They're totally made up. And they're just built on mathematical functions. So this is a sine wave and this is a parabola. And again, you're seeing a TSNE plot. So this is the two-dimensional projection of this high-dimensional data, where each of these points corresponds to another dimension. And so these two kind of clumps that you see here correspond to what I call the boring classes. So 99% of the data comes from one of these two classes. And these clumps in the middle that are like a little bit separate from the others are the anomalous classes, which make up 1% of the data. We've got a step hat and a Gaussian, and this is a sum of sine waves. And so I designed this experiment where I hypothesized that this is the most interesting object that I've ever seen. This one is terribly boring. It's some instrumental artifact. And I'm ambivalent about this one. It's kind of interesting. Okay. So then I used exactly the same interface. So you can see Astronomy running on this transient-like data instead of images. And again, I'm showing you I'm stepping through some random examples. And so you can see, not surprisingly, pretty much everything we're seeing are the ones that belong to these two most common classes. Okay, so then if I run the anomaly detection algorithm, it looks a lot better. Now the anomalies are ranked very highly. And so if I only went through 100 objects instead of all 50,000, I would find a lot of anomalies. But the problem is, you can see there's a lot of these ones, which I said were the boring ones, or the ones I didn't care about. And I don't see any of those sum of sine waves that I'm interested in. So I went through about 100 and labeled them, where I gave the sum of sine waves, this class of 5, that class of 3, and that class of 0, and then ran the active learning. And now if you step through the ranked list, you see a few of the ones that I was kind of ambivalent about, but you start seeing the sum of the sine waves. So you're able to really, really quickly prioritize the objects that you find interesting. Okay. So I just want to explain how we do this, because it is quite a novel approach to active learning. And what's really nice about it is you can get away with labeling only a very small amount of data, and you can start seeing pretty good results. So a little bit of maths. This is basically, okay, let me take a step back. With our active learning approach, what are we trying to achieve? Okay, we're trying to take this anomaly score, which is like the raw anomaly score that comes from the machine learning algorithm, and we want to weight it. We kind of want to moderate it. And if the user finds these kinds of objects really interesting, we want to upweight them. And if the user finds these objects really boring, we want to downweight them. But what we also want to do is, if we're in some part of a data space where we don't have any labels, so we don't know whether the user likes this or not, but an anomaly appears there, we want to make sure we show that. We want to make sure the weighting of that one stays high, because we don't want to miss anything, right? So there's this combination of combining the machine learning score with the user relevance score, but also with our uncertainty about what the relevance actually is, so about what the user labels on. And this is the equation that, or an equation, there's many possibilities, that is able to do this. Okay, so this is our final score that we end up with. And if we rank the data using this score, then we should hopefully see more interesting anomalies or more relevant anomalies. So what are you looking at? This is the original anomaly score that comes out of the machine learning. This is a distance penalty term, which I'll show you in a second. And this is the predicted user relevance score. This should be relevance score. Okay, what do I mean by this? I mean that the user will label some objects as, 5, very relevant, or 3, or 0, or whatever. And then we try to predict the relevance in the rest of the data space. And we do that with another regression, so another machine learning algorithm. And this term basically incorporates the uncertainty in terms of how good we think this prediction is likely to be. Okay. And this distance penalty term is given by this. So it's an exponential of the distance to the nearest label. And these are tuning parameters. This is the average distance, and this is a tuning parameter of order 1. Okay. So what does this mean? If the distance is very, very large, that means this becomes a large number, and this part tends to 1. So we end up with just our original input anomaly score. Okay. But if this becomes very small, this delta tends to 1, and this part of the equation disappears. And we end up with our anomaly score moderated by the user relevance score. Okay. So I tend to not think in equations. There are probably many in this group that do. I tend to think more in pictures. So for those of you who are like me, this might be easier to digest than the equation. So what are you looking at? You're looking at another visualization of the high dimensional data space in 2 dimensions. Okay. So that's what we're seeing in these plots. And I've colored the area by anomaly score. So if it's light, it's got a very high anomaly score in that region. If it's dark, the anomaly score is very low. Okay, so what you can see immediately is, after running the machine learning algorithm, any object that appears around here thinks is very anomalous. And here, it's not very interesting at all. What are the little numbers? The little numbers are the labels that I, as a human, have put in. So I went through the data and I looked at a bunch of objects, and the ones that I really liked, I gave 5s. The ones that I sort of didn't really mind, I gave 3s. And the ones that I really thought were very boring, I gave 0s. Okay. And now you can see the original anomaly scores were very high around here, but I'm not interested in those. When I apply this equation, this is the resulting anomaly score. Now you can see that the things that have been given a 0 have been seriously downweighted, and the anomaly score is now very low. And it's not just immediately near those objects, it's in this whole region, because it's learned that this is an irrelevant region. And the 5s, you can see that whole area has really kind of lit up and is now got a much higher rating of anomaly score. And then, of course, the 3s sort of stay roughly the same because they're kind of somewhere in the middle. So the idea is that if any new object crops up that has a really high anomaly score according to the machine learning, it's just going to get down-weighted thanks to this. Okay, so I'm running out of time. So I just want to finish off with 2 more examples just to kind of demonstrate that we've also run this for some MeerKAT data. So this is now radio data. And again, this is a random sampling around an image where most of what you see is kind of noise or point sources. But if you run some anomaly detection, then you start seeing some very pretty radio galaxies. And just to highlight a few here, I particularly like this one and this one. And then I just also wanted to highlight this, the student Sarah Webb. She's another very, very bright student and is actually looking for postdocs. And she was one of the early users of Astronomy, and she applied it to this deeper, wider, faster program, these fast transient light curves that she had. And she also applied some clustering because this data had never been looked at by anyone. She had thousands of light curves. And so was using unsupervised learning to make sense of it. And she actually published her paper before the Astronomy paper came out. I think this is a consequence of becoming faculty, is that all the students are so much faster than you are. So anyway, so Sarah did a really great job in figuring out what was boring noise, what was instrumental effects, and what were actually interesting objects. I'm not a variable stars person, so I don't really know much about the things she found, only that she found a bunch of variables that were known. She discovered a few new ones, and she discovered this ultra-fast flare star, which is apparently quite unusual. Anyway, it worked. And then the final thing I just want to mention is by another very bright student, Daniel Mutakrishna, who is at Cambridge, because one of the problems with Astronomy is it's designed to work on a data set that's already in existence, right? But for something like Rubin Observatory, we're going to have data coming out live. So we need to be able to do real-time anomaly detection. And so we developed, I won't go into the details, but an anomaly detection algorithm that could operate on live data. And you can see that if you look at this anomaly score, everything seems fine, but then the anomaly score kind of shoots up because it really just doesn't know what this object looks like. And that was quite good because this is real ZTF data. This was a peculiar 1A, so it was indeed an anomalous object. Okay, so that was my whirlwind tour around anomaly detection and some of the cool applications that we're doing. So I think to conclude, machine learning really is becoming a very non-optional, very critical tool in handling the amount of data. And I'm particularly interested in how we do this, the problem of making new scientific discoveries in this era where so much of the data won't even be looked at. And if you're interested in Astronomy, the paper just came out. The code is publicly available. And I just wanted to take the opportunity to advertise the Supernova Foundation, which is a mentoring program I run for women in physics. So for any women faculty or postdocs or students who want to sign up as a mentor or mentee, please just visit the website. And yeah, and there's my email address if anyone wants